Hey everybody, we have a little more relativity work to do. So I wanted to begin by having you open up the next homework that the handout that I've put up in the portal. Here's a view of it. There are a couple of problems here. Each one has some features that I want to discuss. This first one is to try and help you understand the size of the effect of relativity when we're traveling at speeds that are common to us. 200 miles an hour is pretty fast in our world. But in terms of relativity, it's a very, very, very slow speed. And so this problem is supposed to help you determine and calculate the smallness of the effects of relativity in everyday life. It's only when you get to go very fast that special relativity becomes an issue. So here's the issue. We have a NASCAR, an automobile racing at 200 miles an hour around the track. The car is measured at 4.5 meters in length, which is 1.5 times 10 to the minus 8 seconds. I can record the length either as a meters number or as a seconds number, a time for light to travel 4.5 meters. And we're going to measure the car in a frame of reference where it's stationary, and we're going to then measure the length of the car in a frame of reference where it's zooming around the track at 200 miles an hour. And the question is, how much shorter does the car appear when it's measured moving fast? Because moving objects are shorter. And in the process of doing this calculation, we're going to have a beta, a dimensionless velocity, that is an extremely small number. And when that happens, your calculators are going to have trouble, or at least that's a potential problem. So what I'm going to do is encourage you to test your calculator to make sure that it really works well when you have a small beta. Here's what I want you to do. First, we'll make the diagram for the problem and set it up, and then we'll deal with the calculator issues. And the simplest answer in terms of the calculator is if you have a PC, if you use the built-in calculator in the PC, it shouldn't be a problem. Many calculators have a round-off issue when you get to numbers that will occur in this problem. And so if you use a handheld calculator, it probably won't be effective. You won't be able to do this problem with a handheld calculator. You'll have to use the computer. Some versions of Excel work well, some don't. You just have to try it and see. If you're in doubt, you can certainly go to a website. There's a calculator online called Calc 2.0. You can look that up, Google that. You can also go to a website called Wolfram Alpha. And there's a calculator there which can show lots of digits. Just look for the switch that allows it to show more digits. And you need to be able to go out to like 20 digits or more, 20 decimal places without rounding off in order for this to work well. So you just need to make sure that your calculator, whatever you're using, can do that, and then you shouldn't have any trouble. So let's do the setup for this problem. We have an object whose length we're measuring. When we do length problems, we have to have two world lines, one for the front of the object, one for the back of the object. So let's go to our diagram. And since this is a problem that's not going to match one of our special diagrams with the grids, I'm going to use the one that's just a blank sketch. There we go, right here. I'm going to use this one. So I would encourage you to pull this up in PowerPoint And let's just put some lines on here. So here's the world line. And before we do the world line, let's choose our reference frame. So let's do this. Let's say the perpendicular reference frame is going to be the track, and the moving reference frame is going to be the car. And in the reference frame where the car the car is moving around the track, okay? And in its own reference frame, the car is not moving. So we're going to put world lines there's one world line. There's another world line. And these represent the front and the back of the car. And we know the length of the car in the reference frame where it is not moving. So let's put that information in. In the reference frame where it's not moving, that would be in the skewed reference frame. Why? Because the simplest answer is because the world lines are parallel to the TM axis. We've chosen to make the car stationary in its own frame of reference, and that's the way things are. This is a delta XM, and we know that that's 4.5 meters. I'm going to use the meters length instead of the time, and it shouldn't make any difference which one we use. And then the issue is we're going to measure the length of the car in the perpendicular reference frame, and in that reference frame the car is moving, and so a person in that reference frame has to put the tape down very carefully, and they have to put the tape down simultaneously. So I'm going to put world line, I'm going to put event dots on the front and the back world lines of the car at the same time in the perpendicular reference frame, at the time 0 line. And what that tells me is that delta TS equals 0. And if I look at my Lorentz equations, that's going to give me a Lorentz equation that says delta XM equals gamma delta XS. And I need to measure the distance between these two pieces of tape in the perpendicular reference frame. This would be a delta XS, and that's what I'm trying to calculate. And if I look at my equation, I'm going to need to do a little bit of algebra on that equation and solve for delta XS. So if I do the algebra on that equation, I'm going to get delta XS is delta XM divided by gamma. And now here's your calculator issue. Gamma is the square root of 1 over 1 minus beta squared. And beta is 200 miles per hour divided by c. Remember, beta is a dimensionless velocity of the skewed observer. Well, the car is traveling at 200 miles per hour, so that's the dimensional velocity of the skewed observer. To make it dimensionless, I have to divide by the speed of light, c. And now I have a units mismatch because c is in meters per second, and the miles per hour is a different set of units. I would need to convert the miles per hour to meters per second and then divide. And you're going to find that beta comes out to be a very small number. And when you square a very small number, because that's what the equation says to do, you square it, then it becomes even smaller. And so gamma is going to come out to be very close to 1. It's just going to be a little bit bigger than 1. But that little bit bigger is the effect of relativity. If gamma equals 1, then there is no relativity effect. Remember, gamma is a relativity correction factor. If gamma equals 1, there's no correction. If gamma is just a little bit bigger than 1, then that little bit is all the correction of relativity. That's what we're trying to figure out. And you're going to need to have a calculator that can calculate a number like 1.0000000 out to like 14 decimal places. And then you've got to get like 6 digits after that. So you need to get like 20, 21, 22 decimal places. And so you have to make sure the calculator you're using can do that. Right? Otherwise, you're not going to get a right answer. If your calculator rounds things off, it's going to be wrong. You're going to get a wrong answer. And then, let me just make this comment. After you do the calculation, you figure out what gamma is, and it'll be just a little bit bigger than 1. It's going to be, gamma. Let me just give you a little clue here. Gamma is about 1.000000. There's 6, 7, 8, 9, 10, 11, 12, 13, 14, 4, ... It's going to be something like that. And you need to get like 6 digits out here. 6 digits. So there's no round off error. Once you get the gamma, you're able to do this calculation and figure out delta XS. And the question on Math Excel is how much shorter is the car because it's moving at 200 miles an hour. So in essence, what I'm saying is you have to do a subtraction problem. You need to figure out delta XM minus delta XS. That's the question that you're being asked to find, the difference in the length between the length of the car when it's not moving, it's stationary, and the length of the car when it's moving at 200 miles an hour. Okay, so hope that's clear. There's the setup, there's the diagram, there's some commentary about the calculations. Right? So there's what we need to do. Now, I'm going to need to delete this to get another diagram for the next problem. So let me just do this. Let me just go here. Let me just use this. Let me zoom in on this a little bit. Let's look at the next problem. The next problem says we have an observer in the lab measures the speed of 2 electrons. One is 0.8 the speed of light, one is 0.9 the speed of light. If the 2 electrons are traveling in the same direction, then how fast is electron A traveling as measured by electron B? So here's the issue here. This is a velocity calculation. So it means that we have to do a slope of a world line. We have to take the inverse slope of a world line. This is not a problem where I have 2 world lines and I'm measuring the distance between them. That's a length problem. This is a velocity problem, and in our studies so far, you've been told and you've learned that velocity on these graphs is the inverse of the slope of a single world line. So we need to draw a world line. So let's go back to our diagram. And let's draw a world line. And let's do this. Let's put down our frame of reference. This is the lab. And this is electron B. Electron B is the skewed reference frame. And the reason is because if you read the question, electron B is measuring the speed of electron A. That means electron B is an observer the term observer means somebody who's making a measurement. It doesn't mean somebody that's in the problem. Anybody in the problem can observe stuff, but only two people are making measurements at any time in a relativity problem. So I always have to pick the two that are making measurements. And electron A is not making any measurements according to the wording of the problem. Electron B and the lab observer are making measurements. They're my two observers, and they're my two reference frames. And we're told that electron B is traveling at 0.8 the speed of light. So that's the beta, because the velocity of the skewed observer is the beta. The dimensionless velocity of the skewed observer is the beta. So now we can put in a world line for electron A, and there's the world line for electron A. And it's going a little bit faster than electron B, so it has a little lower slope. And I need to figure out how fast it's going as measured by electron B. I know how fast it's going as measured by electron A. The velocity as measured in the perpendicular reference frame is 0.9. That's what we're told. That's a perpendicular velocity. So that means I can do a couple of things here on my drawing. I'm going to make two dots on the line because we're dealing with the slope. And you should always think of slope in terms of two dots on a line. And if I'm measuring slope, I need the rise and the run. So I draw some lines through the points. And this is my rise. This is my run. And notice that the dashed lines I've drawn are parallel to the TS and the XS, because I know these numbers, or I know something about these numbers in the perpendicular reference frame. So I'm going to draw grid lines that are in the perpendicular reference frame, which means they're parallel to the perpendicular axes. And now I'm going to say that the rise is 10 seconds and the run is 9 seconds. And the reason I'm choosing those two numbers is because the inverse of the slope, right? The slope, look here, slope is 10 over 9. Velocity equals 9 over 10, which equals 0.9. And that number is what I was told is the velocity of electron A as measured in the perpendicular reference frame. I wasn't told these numbers, rise and run. These I made up. But I didn't just pick any two numbers. I picked the two numbers that gave me the velocity that I was told. The numbers I choose had to be consistent with the information that I was given, that the velocity is 0.9. Even though I made them up in such a way that they were not going to cause me any trouble by being inconsistent with the information I was given. And now the problem is that the electron B is going to measure the same two dots on the same line. Observer electron B is looking at the same thing, the world line of electron A, and they're going to look at the rise and the run between the same two dots, but they're going to get different numbers because now I have to do lines like this. Those are the grid lines. This is the run, and this is the rise in the skewed reference frame. And you can see that they're different. Okay? These grid lines have to be drawn parallel to the skewed axis lines. And I need the rise and the run in the skewed reference frame. Well, That's precisely what my Lorentz equations were created for. My Lorentz equations were created to do that. So let's put it this way. This number here is a delta TS. This number here is a delta XS. This number here is a delta TM. And this number here is a delta XM. Here's my beta. You can use that to calculate gamma. I have a delta TS and a delta XS. I can use those to calculate delta TM and delta XM using the Lorentz equations. And then velocity in the skewed reference frame is delta XM over delta TM. So use the Lorentz equations to calculate delta XM and delta TM, and then take their ratio, and that will give you the velocity of electron A as measured by electron B, the skewed observer. Okay? Now, the second question says, what if electron A is going in the opposite direction of electron B? Let's take a look at how that would change things. I'm going to extend my axis line back this way. I'm going to make a new world line for electron A. This is now electron A. This is electron A moving to the left, whereas this is electron A moving to the right. The first part of the question is asking if electron A and electron B are moving in the same direction, and I'm going to say that's to the right. Then we get the problem that we just worked on. The second part of the problem says, what if electron A is moving to the left? Well, here's the diagram for that. I draw the world line so that electron A is moving to the left. Then I've got a dot, and I've got a grid line. This is my run. This is my rise. This is a delta XS. This is a delta TS. This is going to be 10 seconds, and this is going to be minus 9 seconds. The minus sign is everything. Because we're moving to the left, the run is minus 9. That's crucial. Then we do everything exactly the same as we did before. We have the beta. The beta has not changed. The beta is still 0.8. Electron B is still moving to the right at a speed 0.8. But I have a new delta XS. My delta XS is now minus 9 instead of plus 9. That's going to make a huge difference in my Lorentz equations. So plug in this delta XS of minus 9 and this delta TS of plus 10. This is still positive 10. Plug those numbers into the Lorentz equation and calculate a delta TM and a delta XM, and then again take the ratio of the delta TM and the delta XM, and that'll give you the velocity. But now it'll be the velocity of electron A moving to the left. And remember something. No physical object can travel faster than the speed of light. Here we have electron B moving to the right at 0.8, 80% the speed of light. We have electron I'm sorry, electron B moving to the right at 80% the speed of light, electron A moving to the left at 90% the speed of light. And yet when electron B measures the velocity of electron A, it cannot be going faster than the speed of light. It cannot even be going the speed of light. It must be going slower than the speed of light. And this is relativity. You would expect a number like 1.7 times the speed of light for electron A moving to the left. You know, if two cars are passing each other in opposite directions on Route 7, one's going 50 and one's going 60, they look like they're going 110 compared to each other because they're going in opposite directions. So you would expect to add the two velocities here of the electrons and get 1.7 times the speed of light. But relativity theory says nothing can go faster than the speed of light. Nothing can even go the speed of light except light. And so you work it out and see the difference. Okay. So let me just make a comment. We got a test coming up soon. Here are the things that you have to know for the test. You need know how to do length contraction. This is the distance between two world lines. You need to know how to do time dilation. This is the time between two event dots. And you need to know how to do velocity transforms. Inverse slope of one world line. Right, those are the big ticket items that we've been covering. So those are kind of categories of problems that you need to be able to kind of look at the patterns of how you solve these problems. And the homework should help you do that. But you should begin taking that information and compiling it into some kind of a summary for yourself to get ready for the test coming next week. Okay, hope this has been helpful. See you next week. Have a good weekend.